In this example, we're asked to compute the surface integral of f ds. So this capital S is the surface area element. So we're going to integrate over a curved surface in R3 of a function, which all we know about the function is that it's equal to, so it only depends on this value of the square root of x squared plus y squared plus z squared. So that's like the radius of a sphere, the rho in spherical coordinates. And we're told that the value of this function at this one point, at g of 2, is equal to -5. And we want to evaluate or calculate this integral over this portion of a sphere. So it's the entire sphere, actually. So S is the entire sphere. So the first thing that we need to do is we need to parameterize the sphere and figure out what's going on with the surface, and then we can call in this function f. Okay? So we have parameterized the sphere before. We calculated the surface area of a sphere as a parametric surface in the last chapter, last section I should say. And so I'm just going to sketch the sphere just to remind us, because the sphere is very important. And spheres, obviously, I think you can probably guess, we're going to use spherical coordinates to do this because it's the obvious thing to do, right? Spherical coordinates just automatically trace out spheres in space. So the first thing that we want to do is we want to make sure that this sphere gets out to a radius of 2, okay? So the radius is fixed. So what we do in the rho direction, we make sure we get out to rho equals 2, and that is a constant, okay? That's a constant. And then once we're out here in the z direction to this point, then we have to rotate, let's change the color here, then we have to rotate that point around. Okay, and so this is our angle, what we usually call phi. Phi goes from 0 to pi, and then once that's done, then we can rotate the rest of this around the angle theta from 0 to 2 pi. And in terms of the parameterization, our phi theta domain, this region, this domain, is actually just a little rectangle, right? So it's a rectangle that goes from 0 to pi in the phi direction, 0 to 2 pi in the theta direction, and then traces out this, obviously fills out this rectangle, which we'll call D. All right, and so the question then is, what's R, right? What is R? And we can compute this. So our R is going to be a function of phi and theta, and as a parametric function, it's going to be, our rho is fixed at 2. We're just going to use spherical coordinates here. So it's going to be 2 sine of phi cosine of theta, that's spherical coordinates. Y is going to be 2 sine of phi sine of theta, and z is going to be 2 cosine of phi. All right, and then what we need to do if we're going to integrate with respect to surface area is we need to compute the surface area element. Okay, so we've done this in a previous video, but I'm going to do it again here just to remind us. So remember, the surface area element is the length of the normal vector with respect to phi and theta times, in this case, just d phi d theta. We know it's going to be that because this is a nice rectangular region. You can have, this is really just the area element in the parameter domain, so you don't have to use it as just a product of these two differentials. You can change coordinates over there if you need to, right? But anyway, this is right. So what we need to do now is focus on this normal vector nu. All right, so remember that nu of phi and theta is equal to the cross product of r sub phi with r sub theta. So I'm going to just write these out. Here's our function. So r sub phi, this is the phi derivative of our vector function r. So it's going to be 2 times cosine of phi times cosine of theta. So 2 cosine phi cosine theta, and then 2 cosine phi sine of theta, and then -2 sine of phi. So there's the phi derivative. We now do the same thing with the theta derivative. So this is going to be -2 sine of phi sine of theta, -2 sine of phi, this one's +2, sorry, +2 sine of phi cosine of theta, and then 0. So theta, there's no theta here. All right. Now at this point we have to take the cross product. So I'm going to leave myself a little more room for this. Start over here. And the cross product is going to be, in the first component, it's going to be 4 sine squared phi cosine of theta, it's squared. In the second component, it's going to be positive, again, 4 sine squared phi sine of theta. And then in the last component, it's going to be 4 cosine phi sine phi times cosine squared theta plus 4 cosine phi sine phi sine squared theta. And at this point, there's a whole bunch of reduction that can be done. Well, we need to take the length of this thing, right? And all the reduction happens when we take the length. One of the reductions that happens before we try to take the length is here. We notice that we have a Pythagorean theorem here. The cosine squared plus sine squared factors out, right? Or really, we should say the 4 cosine phi sine phi factors out. The rest of it's just 1. And so what's left here is just 4 cosine phi sine phi. All right, so we'll use that. Now what we need to do is compute the length of this normal vector nu. And I'm going to do the length squared because it's almost always easier. And I'm going to group this, okay? So when I group this, look what we have here. We have, again, a Pythagorean theorem with respect to the thetas. So each of these is going to have a 4 sine squared phi, all right, times, squared because you have to square that. Then what's going to be factored out is a cosine squared theta plus sine squared theta. All right, and then over here, this whole thing just gets squared. That has to get added, right? So this is going to be then 4 squared cosine squared phi sine squared phi. And of course, that's a 1, so that's gone. And a little bit more reduction here. This we can write as 4 squared sine squared phi sine squared phi plus 4 squared sine squared phi cosine squared phi, a little rearranging. And the whole reason here is, once again, we can factor out these terms and Pythagorean theorem these terms. So 3 Pythagorean theorems here to help us reduce this. And what we end up with is that our length of nu, which this plays a huge role in our integral, is just 16, or the radius, well, sorry, this is still squared, right? So the length of nu squared is, let's write it that way then, so we can easily get rid of the squares. But this is going to be 4 squared sine squared phi, and so this tells us then that our length of nu is just going to be 4 sine of phi. Okay, so this reminds us, by the way, you don't have to do this every time. I've done this twice now for the sphere, but we can remember that the sphere now, the surface area element for the sphere is now 4 sine of phi d theta. Okay, okay, and so now anytime you integrate over a sphere in spherical coordinates, as long as you follow our conventions of how we build the sphere, this right here is the surface area element. Okay, so now we have to go back and remember the original question, which was to integrate this function f over our sphere, and all we know about f is that it only depends on the radius, rho, in spherical coordinates, and g of 2, so the f of 2 in some sense here, is equal to -5. And look at, our sphere is exactly the sphere which satisfies rho equal to 2, right? So actually what we have to integrate up here is just this function can just be replaced with, because we're on the sphere, this function just gets replaced with g of 2, right? G of rho. Rho is a constant, and so that's just a -5. And so our actual job here is to compute -5 times the double integral of the surface area of the sphere, which actually we don't need to do all this work to do this. We can check our work. I mean, it's good to practice this process, right? But in reality, if we were just going to do this as quickly as possible, which is not always the best idea, but this, if we had noticed this to begin with, this would just be -5 times the surface area of the sphere, which is 4 pi r squared, right? So 4 pi times 4, and so this is going to be, what, 80, right? So -80 pi. That should be our answer, but let's make sure we get that in when we do the integral, okay, when we actually compute the integral. We've already done all this work to work out the normal vector, so, or the normal vector in this surface area element, so we might as well use it. So we want to compute the surface area over the sphere of our function f of xyz ds, And we know actually that this function is really just g of rho, right? So ds, so that's one of the assumptions, right? That f of x, y, z is just equal to g of rho. And we know that rho is fixed. So it's really just g of 2 along the surface because that's a property of the surface. And finally, we know that this is minus 5, right? So this is minus 5 times the surface area. And like I said, we know a formula for the surface area of a sphere, but let's work it out. So we've got this formula here. That's what we have to integrate up, right? So this is going to be minus 5. Integral 0 to 2 pi. Integral 0 to pi of 4 sine of phi times d phi d theta. All right, and this can get broken up now. So we have minus 20 integral 0 to 2 pi d theta. There's no thetas here. Times integral 0 to pi sine of phi d phi. And this is minus 20 times 2 pi times, you can work this out, but we can write it down, I guess. This is equal to minus cosine of phi evaluated at 0 to pi. And this just gives us negative 40 pi times, this becomes 1 plus 1, and so we get negative 80 pi. Done two ways. One way, just using the geometry, is much quicker, but you know, we're trying to learn about surface integrals, so using a surface integral we get the same answer, and that's important here. So either way you do it, you get the same answer.